The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees.
Good afternoon. My name is John Stanton from the University of Washington, and I have to admit to being here under somewhat fraudulent pretenses, because even though we used some advanced materials during the development of this system, in the end we used advanced materials like concrete and steel with nothing fancier than that. However, we did it and put together a bridge using some rather unusual arrangements, and it worked very well, so we'll talk about it anyway. Just a quick outline. We'll talk about the new bridge bent system and some criteria that we were trying to satisfy, and then look at the experimental validation and then wind up with some conclusions after that. The problem that we're trying to address is kind of a double problem, one of which is this, traffic congestion. And one of the arguments is that if we use accelerated bridge construction, then we could hope to reduce the congestion, at least due to construction activities. Other reasons for congestion we cannot deal with, but this one we hope we can. And the idea is that accelerated bridge construction, using special techniques to build the bridges faster, will be a critical element in trying to reduce traffic delays. And it also has some side benefits, like if we reduce the on-site construction time, possibly at the expense of increasing preparation time off-site, then we can also get increased worker safety by having people exposed to traffic hazards for a shorter length of time. And also, if we prefabricate pieces in a precasting factory, then we can usually get better quality in the components. We already do this quite extensively, and we make things like precast, pre-stressed girders. So the question is, can we make more of the structure by using precast components? And the cat beams and the columns are typical ones. But in a seismic region, these have some special problems, even though they are the key to the speed of construction on site, of being able to prefabricate things and put them together quickly on site. They still have problems in the regions which we're showing here, where the connections to the cat beam and the footing between those and the column are made. The difficulty is that if we want to make connections, they are almost inevitably going to be at the ends of the column, at the top and the bottom. And this is really dictated by the needs for fabrication and transportation. If you can make a straight element like a column, it's a lot easier than making a cruciform one. But unfortunately, this is exactly where the big moments happen during a seismic event, and the big inelastic action happens. So what you wind up doing is having to design connections which are both convenient to construct, but they're also very resilient in the face of large inelastic deformations. So both things are happening in the same place, and that makes it more difficult. What we're trying to do is to set three goals. One is the traffic problem. We don't want a traffic problem, and so we're trying to accelerate construction. The next one is we would like not to have residual displacements after an earthquake, get rid of that, so we're trying to minimize those. And then the last one is, here we see some serious seismic damage. We'd like to get rid of that and reduce the column damage and try and do all three of these things at once. So that's where we were trying to go. If we look at the accelerated construction, what we came up with was the idea that if you dig a hole in the ground, you bring a column along, you tip the column up, put it in the hole, you put the footing steel in there, and then you cast a cast-in-place footing around the column with no steel whatsoever extending from the column into the footing. You see we got some bars sticking out of the top, and so we come along with a grouted connection to the cat beam. You drop the cat beam on, and then come along with the girders, and then the cast-in-place deck to stitch the whole thing together. Now the bottom connection, which we'll look at briefly, is very simple indeed. You almost saw the whole thing anyway. You take the column, put it in the hole, and cast the concrete around it. And amazingly, it works really well, but it's very, very easy to construct. The top connection, you have to do something a little cleverer, because if you were to cast the cat beam around the top of the column, basically doing the same thing that you did down at the footing, then you'd shoot yourself in the foot as far as the accelerated bridge construction goes. Because one of the best ways to speed up the construction is to use the precast cat beam. So here's the spread footing connection at the bottom. These are in fact test samples. The left one was one we did in our own lab, and the right-hand one is a smaller version which we tested, and I'll show you later in some shaking table tests. And you literally take the column, you put it in the footing, and you can see the footing steel, the top and bottom footing steel there, and then just cast the footing concrete around it. And that's about all there is to it. It has advantages of having very good tolerances down the bottom. If you need to move the column around 2 or 3 inches either way, you can do that, no problem, because you're just casting the wet concrete around it. Up at the top, things get a little bit more complicated, but it's still very buildable. At the top of the column here, we have a steel tube, which we'll talk about a little later from a seismic point of view. And there's a reduced diameter section, or like a peg, sticking out of the top of the column in the middle, and it's roughened on the surface. And then we have rebars sticking up here, which go into their own individual ducts. First of all, you put on a fiber-reinforced grout pad for the cat beam to sit on, then bring down the cat beam, and the individual bars here go into individual ducts, and this peg in the middle goes into a large duct in the middle there. So it's like a kind of planetary system. You have a big element in the middle, and then in a circle around it you have some bars going into their own ducts there. We fill them up with grout, which you can do from the top. And a couple of other things you might notice is that we have this steel tube, which is going to act as confinement in the top. And in addition to that, there is some local debonding here on the rebars, because we do not want them to suffer very large strains at the interface here, which is where some of the inelastic strains are going to happen. So this is a picture, again, of 2 separate specimens. You wouldn't know it, but this one is actually upside down. When we cast and built this one in our lab, what is really the cat beam was down on the floor, so we just turned the slide upside down. And this is the one which was cast later for our shaking table experiments. But in both cases, you can see this corrugated duct in the middle, and then the series of small ducts around the outside, which will accommodate the rebars there. And the same thing is happening over here. And again, the red stuff here, this is just tape going around the bars, so we can debond the bars to prevent those high local strains. So much for the accelerated bridge construction. Those all went together very easily. We had no problems with assembly, and everything fitted, largely thanks to my student Travis Thunstadt, who made all the components in our lab before sending them to the shake table lab. He did a phenomenal job. Minimizing residual displacements. We have a system which is exemplified by our model here. These guys have unbonded post-tensioning in them, and this is a toy which was given to me by a friend in Chile when he saw what we were doing. And he said, "You're just doing this. You can buy these for 50 cents in the store." You can think of these little wooden beads in the legs of the bumblebee as precast concrete elements, and down the middle of them there is a tendon. It's not made of high-strength steel, but it's still a tendon, and in the bottom is a spring. And as you can see, if you push this thing over, then the tendon does not yield, and it just bounces upright again. That's exactly what we're trying to do at larger scale with concrete and steel. This has been done before for buildings, and in fact, we developed the system originally during the PRESS project way back in the 1990s, and now are trying to adapt it to bridges. And so what happens is that if you have a tendon down the middle here and rebars on the edges, then what you can do is you can get an unbonded tendon to behave essentially like this. The rebars will behave in a yielding fashion, and you add them together, and you can get something which gives you this curve here, which dissipates energy because you see hysteresis in it, but on the other hand, it also goes back through zero here, so that you get zero residual drift in the end. And this is the concept which we're trying to follow. The components that you need are an unbonded tendon down the middle here to give you the recentering, and then we have rebars on the 2 sides which will yield backwards and forwards and give you the energy dissipation that you need there. You can do this by post-tensioning, and this is in fact the way we first tried it way back in time, and we also tried it this way for bridges, and other people have done the same thing. And what you would then have is a post-tensioning anchor up here and one down the bottom, or possibly some other arrangement. And you still probably want rebars here to yield and give you the energy dissipation. But we see probably a better way to do this is to pre-tension it. And if you pre-tension it, you'd need to bond the pre-tensioning somewhere, and that would happen in the end here, and that's why we have this peg sticking out of the end of the column. And the strands will be unbonded down here in the body of the column. And if you do that with a bonded and the unbonded strand, then what happens is that you can do all the critical operations, like the pre-stressing, in the plant, and you can get them right. And if something doesn't work there, you throw it away and make another one, but probably you got them right anyway. The second thing is, if you post-tension and you've got anchorages there which are at least potentially susceptible to corrosion. And if the anchorage is up the top here and you've got a deck sitting on here, unfortunately this is exactly where the negative moments happen in the deck, and therefore you may get cracking in the deck and you may get de-icing salts coming in, and so there is a real question of how you deal with the corrosion. And also if you pre-tension, which of course gets rid of this problem, it also means that you're eliminating one extra operation on site and you can do things faster. In fact, if you take this column out to site, the people who are assembling it don't even know that it's pre-stressed. To them it's just a big chunk of concrete and they've got to get the peg in the hole there and the bars in the ducts and they're away. So we believe that this idea of pre-tensioning has some significant advantages. It does mean to say you've got to think out the connection here, but we found that this configuration for the connection works really well. Next thing about reduced column damage, how do we deal with that? Well, that kind of goes with the pre-tensioning and the rocking, remembering, of course, that this pre-tensioning is unbonded in the middle, so the strand will stay elastic. If you have a column which is displaced sideways like this, and you do a conventional reinforced concrete column, you're going to get curvature at the end here, and when you have curvature, you have strain. If you've got tensile strain, you're going to get cracking. And therefore, there will inevitably be damage in these regions here. Tension cracking on this side and crushing on that side. On the other hand, if you make the column act as a rigid body and you allow it to open up a big crack here and a big crack there, then these will allow the unbonded post-tensioning to snap it back into place, just like that extremely exotic and expensive model that we bought, and you can do the same as that. And therefore, if the column acts as a rigid body, there is no curvature. If there's no curvature, then there's no tension strain. And if there's no tension strain, then there's going to be no cracking. What you have done, though, is you traded one problem for another, and the problem that you're inheriting is this one down here. You get some pretty high local stresses at the point where it's doing the rocking, and you have to deal with those. So the way we dealt with that was at the bottom here is our column, which goes down into the hole, and this kind of light gray stuff around it is the cast-in-place footing. And we put a confining tube around here, and the confining tube is about 1/2 of the column diameter long. And then we put this base plate on it, which is just a circular annular plate on the bottom, which helps to do the confinement. And we had to leave a hole in the middle of it so we could get the pre-stressing strands through there. But that all fits quite nicely. And then the idea is that this is going to rock at that interface there. We've got a crack at the interface, and it will rock on this highly confined region at the end of the column. The length of the tube had to be a compromise. We wanted it to be long enough, because you might say, well, why not just send a tube the whole way up and make it into a concrete-filled tube? Well, the answer to that was we wanted to be able to pre-stress these, and if you pre-tension them, you probably have to do it in a horizontal bed. And if you've got a horizontal bed and you make a concrete tube go the whole way up, then you've got a problem casting it. So these had to be short enough that we could cast them horizontally and still be sure of getting good compaction of the concrete in that region, but long enough that they would provide the necessary protection and confinement. And the answer is 0.5000D. Half a diameter seems to do a great job. Here's the original idea for the confining tube. We put the tuna can in there, and this is it in practice. You can see here's the bottom. These are the bars which are penetrating through there, the rebars through. We've not yet put the strand in place. And there is one extra set of bars which are plug welded in here, and those guys go from here upwards. And the purpose of those is twofold. One is to carry tension, that if this concrete decided it wanted to crack there, we don't want a big crack at the discontinuity at the end of the tube, and so these bars will act in tension. And then when the column rocks the other way and those bars go into compression, they will help carry the big local forces from here up into the body of the column, so we could try to reduce some of the big local forces that happen down there. So we tested these, and we did some sub-assembly tests under cyclic loading in our own lab, and then we took them and we built a real bridge in the lab at Reno, and we tested that on the shake table tests. So here we are testing in our own lab, and the way we did this was to have a cantilever specimen, and we could either put the cat beam or the footing down here. They were obviously different configurations, and we tested them as cantilevers with half the column. And so we have a big test machine here which we put a vertical load on to simulate the dead load. And in it we have a channel with a sliding interface which is made of greasy Teflon, so we can get it down to somewhere in the region of 1% friction there, which is small enough for practical purposes, and you can just about see that channel up there. A load cell, everything else on top of it. And then we have a reaction frame and a horizontal actuator which pushes it backwards and forwards there in a series of increasing displacements. We could get up to 10% drift before we ran out of stroke on the actuator, and this is the column at the very end of the testing. And what you can see is that there are some cracks here. Well, actually, you can't see the cracks. What you can see is the red and blue lines which are drawn next to the cracks, because the cracks have all closed up again. You can't see them. This is the tube down here, which is painted with white paint, and we found no damage in the footing here or the cat beam, depending which one we were doing. There was basically no damage to the column apart from these cracks, which you could not see, and the only real damage that we saw was down here. You see these two blue lines? we had an octagonal column for ease of casting, and we had a circular tube. And so what happened was that the octagonal column, at its vertices, it overhangs the tube by a tiny bit, and therefore you have a kind of geometric discontinuity here, which caused us to get some noticeable cracking in a kind of triangle there. I think if we'd had some kind of a transition piece to go down from an 8-sided to, say, a 16-sided figure there, then we would not have seen that cracking. So no damage essentially to the concrete. What we did find was that the strand yielded at about 3% drift, which is exactly what we planned on, and we found that the rebars fractured at about 6% drift, which again was about what we planned on. If we had extended the deep bonding on the rebars, we could have got to a bigger drift if we wanted to, and if we had stressed the strand to a lower stress in the first place and provided a larger number of strands, then we could have had the same pre-stressing force, and it would have had more ability to go to a bigger strain and therefore a bigger drift. So these are the pictures of the low deflection or moment rotation curves from them, and the idea that it goes through zero seems to be true. It recentered remarkably well, going back pretty much through here. The second thing is that it's got almost no degradation of the load right out to 10% drift. So the strength did not drop off at all. 10% drift is an absurdly high drift. You don't need that in practice, but it's nice to know that you've got it in your back pocket just in case. Now this is another specimen we tested earlier, which was not stressed with strand at all. So this actually was a precast one, but it was detailed like a conventional reinforced concrete column cast in place. And here you can see that it does start to degrade out here when you get to 10% drift, or actually before that, somewhere around 7. And the second thing is you get pretty large residual drifts in the sense that when the moment is zero, then the rotation is very definitely not zero. And so that was one of the things that we were really looking for in this system here. So the shake table tests, these were conducted at the University of Nevada, Reno. And in 2005, one of the very first tests conducted on their 3-table set was one that looked like this. And these were regular reinforced concrete columns, 12-inch diameter columns. They had a 2-span bridge, and for various reasons, they made the columns different lengths. So all 3 columns, or all 3 bents, are different heights. And what we decided to do was to make a bridge of exactly the same geometry as this one, except we would use the pretension columns with the intention that we would then be able to compare like with like a pretension column recentering system with a conventional reinforced concrete cast-in-place system. So we followed the same external geometry, and to the greatest extent possible, we made each of the columns the same strength as the comparable columns in these 2005 tests. We got within about 5%. We couldn't do it exactly because the sizes of strand which were commercially available, and when you've got a very small system, you've got numbers of strands, you either have 5 or 6. You can't have 5.3 strands in there. But for practical purposes, they were the same. Now, all of the loading was in fact in the transverse direction, and we did that because longitudinally they got such a lousy lab in Reno that they just don't have 5 shake tables which are all the same, and we could not put an abutment on the end of this. So we decided not to introduce the longitudinal question, and in fact that's exactly what happened in the 2005 test as well. So this goes. This is the 2005 test on the reinforced concrete bridge. You see that? Do it again. Someone's key. What you can see is there was quite a lot of damage at the top here and the bottom. You could see some of the material coming down from there. And if we look at the details, then after they'd been to what they called the 220% design level motion, because the different motions put on it were mostly the Century City motion from Northridge, and they just increased the amplitude, increased it, and the design level motion was declared to be the one that would create 3% drift in a reinforced concrete bridge. So then they just scaled the others up from there. So after the 220% design level motion, a lot of spalling, the spiral was fractured, you can see the fractured spiral here, and the bars were pretty badly buckled, and you would not want to drive over that bridge if you could possibly help it. So what they did in that test was they removed the extra weight they had over the top of the columns on bent 3, which is the shortest one, and then they gave it a couple more tests, and then they had to stop for safety reasons. So if we fast forward 9 years to 2014, this is the pretension bridge. And you can see here are the octagonal columns. We got the tuna can at the top and the tuna can at the bottom, and then the pretension is going up inside it. I would draw your attention to this steel arrangement here. This is a safety frame, which is designed to catch the bridge if it should fall, and the lab manager there is very keen on having it in place. You can watch this guy. And this is exactly the same motion that with the 220% design one for the previous bridge. So in terms of how big that was, the ground motion for that was 1.83 G, and the bridge went out to almost 13% drift, as in 13%. But after it, when we looked at what had happened, there were 3 cracks in the bridge, in the columns. There were 6 columns and a total of 3 cracks. So actually 4 were uncracked. There was 1 crack in one column and 2 cracks in another column. And this is one of the cracks which, again, you could not actually see unless it was drawn on with a blue pencil. There was a tiny bit of damage down here where we described it before, where the corners of the octagon overhang the circle, but we count that as cosmetic. And we also got a little bit of bulging in one of the tubes down here due to the confinement effect. So very quickly then, the residual drifts. The red one, this is residual drift this way. This is the motion number getting increasingly big as time goes by. And here's the 220 design motion, which you can see is basically the pretension bridge goes through with almost no residual drift, whereas the other one, the residual drift gets very big. The peak motions, they were fairly comparable in terms of peak motion, and we should move on, I think, so we can get to the conclusions. After they'd done the same motions that were applied to the 2005 bridge, the lab manager was thirsting for blood, and so they pulled out a near-field motion from Silmar and then the Takatori motion from the Japanese earthquake, which is a real killer, and they pushed those, and they still couldn't knock the bridge down. They still were down in the 0.2 or 25% residual drift at the end. So for the conclusions, the bridge was very easy to construct. We've actually built one successfully on site, except without the pre-stressing. So all of the connections are basically the same, and the stuff which would worry the contractor is the same, and that's been built in the state of Washington. The precast cat beam saves you a lot because you don't need to put up shoring, you don't need to fix steels, formwork, anything else like that. And so this is the thing that really saves you the big time. In terms of total time, the time for constructing the precast bridge in the lab was 1/5 of the time that it took them to build an almost identical bridge using cast-in-place techniques. So this is, of course, not exactly what would happen on site, but it's some kind of an indication. The last thing in terms of the residual drifts, if you look at the brown column here, that's the steel safety frame column. This is after all the testing had been finished, after it's been through the Silmar, the near field, everything, and that's pretty darn straight. And so that essentially is the proof of the pudding there. During the shaking table test, we had essentially no damage here, and this is what happened when they had not gone through as many of the large near-field motions. So it suffered almost no damage compared to that, except we did fracture rebars. And thank you for your attention. This is a picture of what it looked like building at a very high speed. This is what accelerated bridge construction looks like. You can build it in 30 seconds.